It's a rainy, rainy day. May as well do math. What the heck?
Tagon.
So this is not part of the generalization war. I don't have that response provided yet since he just uploaded his super cool new video today. At least at the time that I'm filming this. But this is a response to a previous video that Flammable Maths did about a cool nested logarithm function, and I found it sort of interesting that he didn't solve for that function sort of explicitly in whatever terms he could. And so I'm going to do that today. It's just a mini little video, and here it is. So a few days ago, Jens was looking at a function that looked like this, or at least an integral that looked like this, right? And he wanted to try and explore some of the properties of this indefinite integral, and so he simply said this statement. And so, you know, the integrand is this thing right here, and he's saying this is f of x, but then if you look inside the nested integrand, you see that f of x is inside of itself, so we can simply write f of x as, and I'll just write it as f as he did, so f equals ln of x minus f, so that's sort of the way of replacing the way it's written into a more clean form. Let's see what we can maybe do with that. So we have f prime is equal to x prime minus f prime over x minus f, right? And this is all taking derivatives with respect to x. So we can write this as 1, right? The derivative of x is 1, and we can multiply the x minus f over, and we get that x minus f times f prime is equal to 1 minus f prime. Adding f prime over and factoring out the thing that it's being multiplied onto, we get that f prime is equal to, we get that f prime times x minus f plus 1 is equal to 1. And then dividing over, we get f prime is equal to 1 divided by x minus f of x plus 1. So this is f prime of x, of course, the first derivative of f, whatever it is. So we've been able to sort of put the derivative of the function in terms of the original function itself. That's not bad. Perhaps we can actually solve for what f is explicitly. And it's not very hard. All we have to do is just try and get all the f's to one side of the equation and utilize a somewhat old friend. So we exponentiate both sides, raise e to both sides, and of course we get e to the f is equal to, well, the exponent and the logarithm cancel, and we just get x minus f. So then we add the f to the other side and exponentiate both sides again. Because what does this give us? So we have a sum of powers inside of an exponent, so we can break that up into two different things. So this is e to the f times e to the f, right? But now look, we have something times e to the power of that same thing, which means we should bring in the Lambert W function. Ooh yeah! Alright, so of course that's what we were going to do. It seems so obvious when you're mixing linear things and logarithms and or linear things and exponents. It's pretty much always going to be this, and except when you learn what the real truth is in my next generalization bomb, Papa. This is a ceasefire at the moment. I'm just trying to expand our knowledge. I will come after you again, I promise. So we're going to apply w to both sides, and that cancels this function, so we just get e to the f is equal to w of e to the x, right? Because we apply w to both sides, w gets tacked onto here, and w cancels this, and you just get e to the f back. Then we have to take the natural logarithm of both sides, and we get that this function f is equal to the logarithm of w of e to the x, which is quite interesting. Let's see if maybe we can expand this out in some way. Well, we know by definition of the w function that that x equals w of x times e to the w of x. So if we take the natural logarithm of both sides, we get log x is equal to log w plus w of x, because the logarithm and the exponent cancel. Subtracting w of x over, we get that the logarithm of w of x is equal to log x minus w of x. So replacing x with e to the x, we can say that this is equal to the natural logarithm of e to the x, which is x minus w of e to the x. Right? And now we can actually answer a couple questions about this function in a nicer way. We actually also know remember we just discovered the derivative, right? We know that f prime is equal to 1 over x minus f plus 1. So this is going to be equal to 1 over x minus x plus w of e to the x plus 1. So we just end up with 1 over 1 plus w of e to the x, which is quite a neat little result we got there. You're going to see something similar to this in a video that I'm going to do soon for Wacky Calc Wednesdays that I think a lot of you are going to like. So for example, let's see what the derivative of this function is at x equals 0. Well, if we plug in x equals 0, we get e to the 0 inside there, and e to the 0 is 1, so we get 1 over 1 plus w of 1. Interesting, that's interesting. So if we call w of 1 a fancy Greek letter, maybe omega, you might recognize omega to be precisely w of 1, right? It's the number that makes such that x times e to the x is 1, and it's about 0.567. And this is actually going to be the answer of something very, very fun that we're going to do in the next Wacky Calc Wednesday, or one of the next two. So this was just a neat little exploration. So now let's see if we can actually answer the question that the Papa was trying to do in his video, which was take the antiderivative of this function. So let's see. Since we just derived what this function was in terms of x in sort of a closed form using this special function, the Lambert W function, we know that this is the integral of x minus w of e to the x dx, right? That's what we're trying to solve. And it looks a little daunting, but there's actually a way that we can reformulate this in terms of integrals that we know, which is quite nice. We could either break this up and just do the integral of x and the integral of this thing right here, which is actually totally the way to go. Yes, that's what we should do, actually. That makes perfect sense, so let's just do that. It's actually not daunting, really, at all. So we get this right here. So what I'm going to want to do here is I'm going to want to do a substitution. We already know what this integral is, right? It's x squared over 2 plus a constant, but we'll get a constant at the end. For this, we need to do a bit of a substitution. So we're going to do u equals e to the x. Actually, let's make it a little more succinct. Let's say the natural logarithm of u equals x, so that when we plug ln of u in, I just get u, which tells me that dx is equal to du over u, right? So simple substitution, and so we get, for this specific integral right here, we're not looking at this one anymore, just this one, we get the integral of w of u over u du, which we've done before in another video of mine, and this is just 1 plus w of u all squared. Oh, you can't see that, sorry. Sometimes I forget to look up at the camera. This is 1 plus w of u all squared over 2, and u is e to the x, right? So this is going to be 1 plus w of e to the x all squared over 2. Both plus a constant. I should probably just write it now. And now we can sort of just put these two things together, and we get that our antiderivative of f, which is, this is f, x minus w of e to the x, is precisely x squared over 2 minus 1 plus w of e to the x squared over 2 plus a constant. Now they have the same denominator. Perhaps you could, you know, do a little difference of squares in here. Maybe that would simplify something, I'm not sure. But it would be interesting. But at least you could find, say, the area under the curve. I don't actually even know what this curve looks like, but this is, I believe, the integral that we're going for. And so that was the little addendum that I wanted to add to your video. I hope that's welcome, and it's pretty math nonetheless. I'm coming for you next time, though. It's on. The nuke is coming. Get ready.